Today we're going to continue talking about power series by looking at a particular power series called a Taylor series. A Taylor series is a series that we can build from a function. Taylor series is a series built from a function. A lot of times we'll think of a Taylor series as a polynomial approximation of a function. It's a polynomial approximation of a function near a point. That's the important part. Polynomial approximation of a function near a point. That near a point thing tells us that this is going to be based on derivatives. Here's the good news. You have already started looking, and you have already found in your past Taylor polynomials approximating functions. That's the good news. You don't get here without having previously found Taylor polynomials of degree 1 approximating a function. Because at this point, you've all found the equation of a tangent line. Tangent line is the degree 1 Taylor polynomial approximation of a function near a point. So good news, we're not doing anything new, we're just adding to stuff that's we've already done. It's the same thing that's going to happen in Cal 3. We're not going to do anything new. We're just going to add stuff that we've already done. We're going to be like, all derivatives. Remember derivatives with a function of one variable? Everybody's like, oh, yeah. It's like, oh, well, now there are two variables, and here's how derivatives work. And the thinking is the same. And then we'll be like, oh, remember when we found area under a curve with a definite integral? And you'll be like, oh, yeah. Like, well, now instead of a curve, we have a surface. And so instead of an area, we're going to find a volume. And we're like, oh, so this is boring then. And I'll be like, oh, yeah, totally. You already know how to do it. Same thing, Taylor series. So a tangent line is a degree 1 Taylor polynomial approximation of a function near a point. So let's remind ourselves. So I know we always think of writing lines in terms of y equals mx plus b, which is kind of terrible. I don't know why 0 always has to make itself involved. Why does it always have to be the y-intercept? So the tangent line is given by y equals. Instead of slope-intercept, I'm going to go with a variation on point slope. And I want it to be how we think about linear functions. Here's our starting point. And then we have a slope given by the derivative at that point. When x is equal to c, the x minus c part is 0. And so we add f prime 0 times, and y is equal to just f at c. That's the first thing that we want the tangent line to have. We want the tangent line to have the same value as the function. The other thing that we want the tangent line to have is the same first derivative of the function. If we take the derivative y prime, we get f prime at c. Notice that y prime, the derivative of a constant is 0. The derivative of something times x is just something. This is what we want from a tangent line. The tangent line has the same value as the function. And derivative. We match the value and the derivative at the point. That's all a tangent line is. Starting at this point, so the point and the line, the line and the function agree on that point. All we take from for the tangent line is the direction that the function is headed at that point. So the line matches the function at the point in the value and in the first derivative. What we're going to start doing is thinking of the value as the 0th derivative. So the tangent line, that first degree Taylor polynomial approximation of a function near a point, is the line that matches the function in value and first derivative. The line matches the function in 0th derivative and first derivative. Now, if we take this and put this into a context of a power series, just keep going. The second degree Taylor polynomial will have the same value, first derivative, and second derivative. The third degree Taylor polynomial will have the same value, first derivative, second derivative, and third derivative. We just build a polynomial by matching derivatives. The Taylor polynomial is built by matching derivatives. Taylor line, or sorry, tangent line, but keep going. Once we see how this is built, we see exactly where calculus shows up, not just all this derivative business, but we're building a polynomial where we just add more terms. And so calculus says, well, whatever you're doing, do that forever. So just add an infinite number of terms, your Taylor polynomial becomes a Taylor series. When you write it, it doesn't seem like much. You just write a polynomial, but instead of just stopping the polynomial at the nth degree term, you write plus dot, 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 saying, yeah, just keep going. Then your polynomial becomes a series. And look how fancy things got when we're talking about power series. So Taylor polynomial is going to be built by matching derivatives. It's a tangent line, then keep going. So the Taylor polynomial of degree n approximating a function near a point. I think this book makes it look more like your Taylor series. It uses A instead of C. The notation that I use for Taylor polynomial of degree n is t with a subscript n. So my notation will be t at t sub n of x. I should probably switch to the books. I think they use a p, but I can't remember. I should probably read this book at some point. It's going to start off just like if I look like just like a tangent line. I want the same value. And I want the same first derivative. The quadratic term is going to involve the second derivative, but we have to do a thing to it. So the second derivative at a, then we have to divide by 2. Here's why we're going to have to divide by 2. Then the next term, which will get us the form, in general, it looks like the nth derivative evaluated at the point divided by n factorial. Now we got to remember, we got to think about where that n factorial comes from. And we're making a polynomial of degree n. And remember, when I get to the nth derivative of p sub n of x, I have to be looking at the nth derivative of f. So that n factorial is there to cancel out all the exponents in the x minus a to the n. When we take the first derivative, I multiply by n. This n factorial gets knocked down to n minus 1 factorial. Then in the next derivative, I multiply by n minus 1. And that n minus 1 factorial gets knocked down to n minus 2 factorial. Eventually, I take n derivatives. The x minus a to the first goes to x minus a to the 0 power. And we're just looking at, and the n factorial is going to be canceled out. And we'll just be looking at f, the nth derivative of f at a. So when we want to indicate the nth derivative of a function, we just put whatever derivative in parentheses so we don't confuse it with an exponent. Newton had a great mind, but not for notation. So we got f prime, that's our first derivative. F2 primes is our second derivative. Then we put 3 primes, then it starts to get a little bit awkward. Because it's like we have to put 4 primes, which is weird. And then how would we indicate that there's just some generic number of primes? We can write this in summation notation. And here's where we're going to have to rely on calling the function itself the 0th derivative. So here's our sum. I goes from 0 to n. So we start with I equals 0. That would be the 0th derivative of f at a times x minus a to the 0 power over 0 factorial. Remember, 0 factorial is 1. X minus a to the 0 is going to be 1. And the 0th derivative of the function is just the function. Remember the specs that we want. I want the nth derivative of Tn of x to be the value of the nth derivative of the function. So that was our original spec. I want a polynomial that agrees with the function at x equals c, all derivatives. Let's make sure that that happens by building Tn of x. If I plug in c into Tn, Tn of c should equal f of c, and that's what happens. So if Tn of c is f at c, and then all the rest of the terms zero out. This is what we wanted to have happen. The value of the polynomial is the same as that of the function. If we take the derivative, the first derivative of Tn of x, the derivative of the constant term is 0. So I end up with f prime at c times x minus c to the 0 power. So my new constant is f prime at c. My next term, the 2 multiplies by the half and cancels out. And I get f double prime at c times x minus c to the 1 power. In my next term, 3 cancels out the 3, but leaves a 2 factorial. So my next term is f triple prime at c over 2 times x minus c squared. This last term, the n cancels out, and I still have the nth derivative at c divided by n minus 1 factorial times x minus c to the n minus 1. This will remind us of why that factorial has to show up in the denominator, because when we take all these derivatives, we've got to cancel out the new exponent that shows up. That's why it's n factorial, because we're going to cancel all those out, so it just leaves the derivative part of the coefficient. And that's why we need the factorial, because I got to cancel out all of them. Now when I calculate Tn prime at c, I get just f prime at c plus 0 for the rest of the terms. Because all the rest of the terms have an x minus c as a factor. And when x is equal to c, x minus c is equal to 0. Let's go one more. The second derivative of the Taylor polynomial. Now the constant term with the first derivative, that cancels out. And I take the derivative of f double prime at c times x minus c to the first. So I multiply by 1, I get f double prime at c times x minus c to the 0 power. So that first degree term is now the 0th degree term. The derivative of the third degree term, the third derivative term, the 2 multiplies by the 1/2 and cancels out. And then we reduce the exponent by 1. In the second derivative, for the last term, the n minus 1 cancels the n minus 1, and that leaves n minus 2 factorial. Just like with all polynomial derivatives, the constant derivative constant is 0. The first degree term leaves behind a constant. The second degree term becomes the first degree term. Everything drops down by 1 power. We got to cancel out all of them as we take derivatives. If we evaluate the second derivative of the nth degree Taylor polynomial approximating f of x near x equals c, all I'm left with is f double prime at c plus 0 for the rest of the terms. For the same reason, they're all going to have a factor of x minus c. And when x equals c, x minus c is 0. In the next derivative, f double prime of c, that cancels out because it's constant. The first degree term, x minus c to the first times f triple prime at c, that becomes the new constant with f triple prime. And so the third derivative of the Taylor polynomial at c is going to be f triple prime at c. And this keeps going all the way down to the nth degree or nth derivative of the nth degree Taylor polynomial. And that's just going to leave behind the nth derivative of f at c. At this point, the Taylor polynomial is out of derivatives, and so it just says 0 for the rest. Any questions? Taylor series, the whole section on Taylor series, after you do the whole section on Taylor polynomials, section 10.2, Taylor series, you just be like, oh, keep going. That'd be it. I'd have 2 words, maybe 1 example. I take a Taylor polynomial that we found in the previous section, and I just put plus ... at the end of it. So we see that a Taylor series is just a power series with a particularly defined coefficient. This is the Cn, the coefficient in the power series that is Taylor series. Coefficient for the Taylor series is nth derivative of a divided by n factorial. Any questions? Is everybody okay? Tangent line, but keep going. Important to recognize that we're not doing anything fancy or even new. We're just saying, instead of just doing the value of the function and the direction, include the second derivative. Hey, while you're at it, include the third derivative. And then we get to Taylor series, like, oh, you know, remember power series? Yeah, just keep going. It's power series. Plus ... Any questions, comments? Snide remarks? The question you should be asking is, why would we want to do this? These functions are well-known functions, and dude, we have friggin' graphing calculators. We carry supercomputers in our friggin' pockets. Why would we need to approximate a function with a polynomial? Which the typical response is, quiet you, it's on the final. That's why you need to know. I don't know, I have to switch to 40 as an answer. Maybe I should do an entire class that way. I don't think I can do it. I don't have, as experienced as a DM as I might be, accent integrity is gone. So all characters that are in, they just sound like me. I try to use different phrasing and stuff, but they just sound like me. They might start off sounding something different, but they end up just sounding like me. You know what I mean? Same with all my characters. But it's not about doing the voice, so don't let that bother you. What were we talking about? Oh, yes. So we want to understand the construction of a Taylor series so that we could use this when we don't know what the function is. What if we have a description of a function? We don't know what the function looks like. We could suppose that there's a power series near a point and see what the description, what kind of power series the description is going to give us. Let's start with maybe our favorite. Now we've done this problem before, but we stopped at first degree in the polynomial approximation. So here's what we need. I need to take my function. So f of x is e to the x. I need to evaluate it at 0. That's the first thing we need. We need 3 derivatives evaluated at 0 and the value of the function. So the first derivative is just e to the x. F prime at 0 is also 1. This example is brought to you by the letter E and the number 1. The second derivative is e to the x. And the second derivative at 0 is equal to 1. These are all the numerators that we're going to need in our Taylor polynomial. F triple prime at x is still e to the x. F triple prime at 0 is 1. So I put the nth derivative over n factorial times x minus 0 to the n. That's the form that that's the formula that we're going to use for Taylor series. Taylor polynomial is just going to stop at 3 instead of keep going. So I'm going to start with f at 0 plus f prime at 0 over 1 factorial times x minus 0 to the 1. There's the first derivative. Those first 2 terms give us the tangent line, 1 plus x. The next term will be the second derivative at 0 over 2 factorial times x minus 0 squared. And the second derivative was 1. Then the third derivative will be the third degree term will be the third derivative evaluated at 0 over 3 factorial times x minus 0 to the third. So there's the third degree Taylor polynomial approximating e to the x near x equals 0. Note that those first 2 terms is give us the tangent line approximating e to the x near x equals 0. 1 plus x is the tangent line. It's the first degree tangent polynomial approximating e to the x near x equals 0. Another thing that we want to note about what we're doing, we're making a polynomial approximation of a function. That raises a natural question. We've got a process by which we make an approximation. How can we improve on that approximation? Approximation? How can we improve on that approximation? Not approve of an approximation. In the calculus way is just whatever you were doing, do it forever. In this case, that would just mean more terms. We improve the approximation by using more terms. We can improve our approximation by using more terms. Then how many terms? That's when calculus steps in. Infinite. Because calculus's answer is always just do that forever. That's why students love math calculus so much. It's the math class that just keeps saying, hey, see what you're doing? Do that forever. Calculus is about infinity. Rates of change are just a consequence of infinity. Let's take a look at the function e to the x. I'll cover this up. No, I'll cover this part up. What we're going to see is that the more terms we include, the more the polynomial starts to look like e to the x. So the first degree polynomial is just, the 0 degree polynomial is just 1. So that's not a very good approximation. It's really exact, it's right on at 0, but it gets pretty bad pretty fast. So we jump up to the tangent line, and we all know what tangent line looks like at 1. If we zoom in, these things are really close together. The closer we zoom, the closer the line is to the function. But when we start zooming out, e to the x says, no, I gotta bend. And the tangent line's like, oh no, one direction. All we're doing now is just adding more terms, and we see what the form of the term is. We add x squared divided by 2. That takes this parabola and puts this parabola tangent to the e to the x, the exponential, near x equals 0. If I include along with this the tangent line, when we zoom in, we can see that that green tangent line is starting to bend, it stays straight, and so the function is bending away from that tangent line. The parabola has a little bit of bend. So even though the tangent line is not very good between at these values of x, we get improvement with the parabola. And we get more improvement still if we upgrade our second degree approximation to a third degree approximation. Higher degree approximation is closer to the function on a wider interval. We get a polynomial that's closer to the function on a wider interval. The next term will be a fourth degree term. And we can see by the pattern, we're going to have a 4 factorial. And we can add, just keep adding terms. The more terms we add, the more the polynomial looks like the exponential. That means the polynomial is closer to the function on a wider interval. Polynomial approximation is better because it's closer in value to the function on a wider interval. So there's 2 avenues of improvement. The approximation can be close to the function, and it's useful over a wider interval. Once we include an infinite number of terms, then we're looking at a power series. The power series should be closer than any polynomial to the value of the function on a wider interval. But since we're dealing with a power series, and since we're dealing with an interval, you could probably guess what's coming out. The interval of convergence for that power series is going to be the interval where this approximation is useful. So here, with this third degree approximation, we can see that we're pretty close from -2 up to 2. Oh, it goes a little past 2. It's pretty good. More terms will bring that polynomial close to the function on a wider interval. Notice that our tangent line, we have to zoom in pretty close to keep the line close to the function. This is a really good approximation between -0.05 and 0.05. But between -0.1 and 0.1, the tangent line is starting to show some space. And between, let's say, -1 and 1, the tangent line is kind of terrible. And we're not that far from 0. We're 1 unit away from 0. And the tangent line is like, oh, man, this is really terrible. Any questions? We improve the approximation by adding more terms, going to a higher degree. Improving the approximation means the values will be closer to the function, and it'll be an appropriate approximation on a wider interval. Any questions? Where that I have, for graphing calculator purposes, I don't use my actual graphing calculator. The problem is the Desmos is just a better graphing calculator. I mean, obviously, the TI-84 was, built in the 90s. So a current machine from the 21st century, clearly it's going to do better, right? But there are some things that I'd have to get a whole separate app. Wolfram Alpha is just bad at some things. I mean, it can do it, but it just takes too long. So I kind of keep my graphing calculator around, my TI-84, I keep it around. Not for graphing calculator stuff. Graphing calculator stuff, I'm just going to use Desktop. But if I'm going to do some linear algebra, I'm going to want that calculator around, because computers in general, the interface is terrible for finding the reduced echelon form of the matrices, which is something that I'm going to do a whole crap ton of linear. Well, I'm not going to do it anymore. When students are in linear algebra, they're going to be finding the reduced echelon form of a matrix a whole crap ton. And you're going to want a fast and efficient way to do it. And that's going to be your graphing calculator, even though I mean graphing stuff. You know what I mean? Weird that we refer to the graphing calculator by the thing that we don't want to do with that anymore because we have a smartphone and compute board. All right. That's what we want to look at for Taylor polynomials. There are some Taylor series that we need to recognize on site, like this Taylor series for dx. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.